friends. Today we really start the topic of the class in terms of connections between science and matters of Christianity. And what I'm going to do is I'm going to be using a set of notes that is almost identical to the ones you have in the website, but a bit more flashy, something that I have used when I go to Europe. So today's presentation is called, hey, linear is best, use the hypotenuse. And this goes long distance to people at Focus. So I hope that it will be a good lesson, not only here, but in Colorado. Okay, so this is the dedication of the lecture, which is, as you can see, already very explicit. To reconcile the world in Jesus Christ, for only His love is the solution. I'm going to try to show, step by step, that that is the case. That there is indeed one solution that is best, and that has to do with loving one another. Right? So here we go. Today's presentation is based on games, similar to what we did last week in defining dimensions and things like that. Okay? The idea is to learn from these games and draw lessons from them. But before I do that, and given the fact that this has to do with the hypotenuse, even at UC Davis, I have to remind you of what you know, of course. The Pythagorean theorem, something that you have learned as parrots. So here is a triangle, 90 degrees between the two legs. A and B are the legs. The side opposite to the 90 degrees is the hypotenuse. As you can see from my sketch, A and B are equal. So this is an isosceles triangle. And they are going to be equal to 1 unit. So what is the theorem? A squared plus B squared equal to C squared. If you draw a square here, and another square there, and yet another there, the area of the square of the hypotenuse is equal to the sum of the areas of the squares over the legs. That's what the theorem says. So, if A and B are equal to 1 unit, you apply the result and you get 1 squared plus 1 squared is equal to C squared. But 1 plus 1 is equal to 2, so 2 is equal to C squared, therefore C is equal to the square root of 2. Remember you repeating already before, so let's do it again. The root of 2. Come on. The root of 2. So what is the root of 2? Is the distance from this point in the bottom to this point on top. And if you expand, you get 1.4142 dot dot dot. But this dot 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 we don't fully understand because this number is irrational. So whatever happens inside doesn't show any repetition. Alright? So, game number 1. It's going to be easy. We are going to play with modeling clay. So we all kids like to do that, right? So what you have on top is a bar of modeling clay. So you buy the clay and you take it out of the box and it's so shaped as shown above. Of course, you are looking at the clay from the side, so you are not seeing the third dimension of the clay, but that's what it's supposed to be, just modeling clay. There is a vertical line over here. That's the second part of the game. The first part is take the bar of modeling clay out. Second part, cut it by that line. Where is that line? Well, that line is placed so that from the beginning to the line, there is 70% of the mass, so that from the line to the end, there is 30% of the mass. Is that clear? Once you cut it, the following is going to be done. Take this piece, which is the largest, and squash it to the left so that it becomes this rectangle that I'm touching here. Likewise, take the small piece and enlarge it towards the left so that this becomes this. Are we together? Notice the distances that are portrayed there, from beginning to the end, and all of this is taking place up to the middle. Of course, I squash this part, so this height is more than the original. Likewise, I took this piece, the little one, and I enlarged it. Consequently, this is less in height than the original. Yes? Let's compute. So from time to time, I'm going to ask you questions so that you compute things. Okay? So imagine for a second that this bar, the height of it is 1 vertical unit. Clearly, the one below is higher because of the squashing. The question is how big it is. That's a question for you guys. How big is this height? You are thinking, and I'm going to help you. Well, what you are seeing is the bar of molding clay from the side, and you are seeing a rectangle, right? So you see a rectangle, you know the base of the rectangle, right? How much is it? You could read it. The base of the rectangle is a half, right? A half. I'm asking you to compute the height, which I'm going to call h. And the hint is, what about this area? How much should that area be? 70%. That's exactly what it is. I have this area, and I cut it by 70%, so this area is 70%. That's exactly what we did. So the area is 0.7, right? So the area is equal to the base times the height, right? Even people that hate mathematics know that that is the case, right? So you can compute the height, correct? So the height is equal to the area divided by b, but dividing by b is multiplying times 2 the area. So the height turns out to be equal to 1.4 units. Are we together? So 1 unit, 1.4 units. That's what the squashing does at the 70% location. Are we together? Yes? I need to know. Okay? I cannot ask people in Colorado where they are, but I can ask you. So, what about this height? How big should that be? It's less than 1, right? Because it's the enlargement gave something that is less. Well, you just apply exactly the same formula, because what you have on the right is another rectangle. The base is equal to a half. The area is now 0.3. Therefore, the height is equal to 0.6. You're doing good, 0.6. So, 1 vertical unit, 0.6, 1.4. Is that clear? Yes? So, do it again. What do I mean? Take this, cut it in the same proportion. The larger piece, squash it. The smallest piece, enlarge it. And to this piece, do it exactly in the same proportion. Okay? So if you do it again, this is what you get. Right? This piece divides into 2, and this piece divides into 2. Questions. How long is this length? It's a quarter, right? Because it's half of a half. So half of a half, you multiply, and you get a quarter. Okay? Let me ask you now a question. How much modeling clay is here? How much modeling clay is in that first left rectangle. Let me backtrack. How much mass is there in this rectangle above? 70%. Now, this piece comes from there, cutting the one above by 70%. Consequently, how much mass is there in this piece?
Maybe 35.
No. It's not 35. That's a common mistake. The key question is, look, this is 70% of this. Right? That is clear because I'm repeating the same game. So the question is, how much is 70% of 70%?
49.
It's 49%. Multiply. That's good. That's very good because that is what happens when you open a bank account or something that has to do with money. Things get multiplied. So it pays to know that you have compound interest that is obtained multiplying. So that's exactly what we're doing here. Okay? So 70% of this is 49%. Yes? Are we together? Could you explain this to grandma? Okay. Maybe to your friends? Maybe to grandma. What about this piece here? How much mass is there in this piece? In the same way, this is 30% of this. So this is 30% of 70%, which is 21%. Right? How much mass is there here? It's also 21 because this is 70% of 30%. Of course, 70% of 30% is the same as 30% of 70%. 21%. And how much is there here? 9%. Right? So this is 30% of 30%. You multiply, you get 9%. Right? 49 plus 21 plus 21 plus 9 is equal to 100%. This is one of the most important principles in physics. Is the principle of conservation of modeling clay. Well, of mass in general, but in this case the mass is made of modeling clay. Is that clear? Shall I do it again? So you do it again. So this divides into 2, this divides into 2, this divides into 2, so on and so forth. If I say to you dot dot dot, I have a sense that you understand what is going on. Is repeat this thing again and again and again forever. Right? That's what it is. There is a formula here for the height of this rectangle after you have done this game 3 times. Once, twice, 3 times. So the question is, can I compute the height? Well, it is still a rectangle, it's going to be exactly the same. The idea is that, question, what is the length of this base of this rectangle? How much?
1/8.
1/8. Right? Because it's a half of a half of a half. So that's 1/8. And then I ask you, how much modeling clay is there in this piece? Well, you ask for this piece. This is 70% of 70%. This one is 70% of 70% of 70%, which is the same as 0.7 cubed. Okay? So basically, you get 1/2 cubed, 0.7 cubed, and the height turns out to be 1.4 cubed. Okay? By the way, as shown, 1.4 cubed is larger than 1.4, and is larger than this height. Any guess? How big is this height? That turns out to be 1.4 squared. Okay? Again, same formula. 0.7 squared, 1/2 is squared, so you get 1.4 squared. Right? So, this game, let's baptize it, is going to be the game of imbalances. And it's easy to remember with your hands. There is one side that is going to be more than the other. And we are going to repeat this thing again and again and again and again in trying to study what is it that happens out of this silly game. Okay? So, a little bit of math. I promise not to bother you much from this. The choice of 70-30, we'll see later, is a good choice. It's a choice that nature selects. It's a choice that has to do with inequalities of wealth, as we shall see later. But it doesn't need to be 70-30, it could be PQ. So I'll do this quickly. PQ, how much mass is there here? Oh, P of P. How much is P of P? P squared. How much mass is there here? Oh, it's Q of P, so PQ. PQ, Q squared. So, P squared twice PQ plus Q squared. This should ring a bell of things that you have seen before. I'm doing this quickly so that you realize that you can compute. Okay? I don't want to spend the time doing the calculations, but things can be computed. At the level shown here, which is at the third level, what you get turns out to be the expansion of P plus Q to the third power. So for those of you that remember, P plus Q to the third power is once P cubed, 3 times P squared cubed, 3 times PQ squared, and once Q cubed. If this sounded horrible, that's okay. All I want you to know is that this could be done, and that this is associated with something that is very well known in mathematics, the notion of Pascal's triangle. Remember Pascal's triangle? By the way, this was not discovered by Pascal. It was discovered by Chinese people way before Pascal. But, you know, Pascal was at the right place at the right time, and he got the credit for this thing. So these numbers that appear here are basically counting how many rectangles are there of different heights. Okay? So let me repeat. There is one, which is the initial bar of molten clay. There is one P and one Q. There is one P squared, 2 PQ, and 1 Q squared. There is one PQ, 3 P squared cubed, 3 PQ squared, and 1 Q cubed. And so on. This continues forever. Alright? So, in physics, because by the way, this is physics, even though it appears to be just mathematics, this game has a name, and this name is known as a multiplicative cascade. Usually, when names are given, sometimes they are very good, and I hope that you realize that this is a very good name for this thing. It's a cascade in the sense that it starts and repeats and repeats and repeats and repeats, right? And it's multiplicative because everything you want to compute, you do it multiplying. Okay? A half of a half of a half, an 8. How much is there here? You just look at where it's coming from. Left means P, right means Q. So this is P, Q, P. So this is P squared cubed by multiplying. Where is this coming from? Another example. To the right, Q, this one is to the right, Q, and this one is to the right, Q. So this is Q, Q, Q. So this is Q cubed. Right? Okay? So, do it 12 times. Of course, the question is, have you ever seen something like this? Probably you say, no, I haven't seen anything like that. Okay? It's not in the phone, eh? It's not in the phone. So, you remember 1.4, 1.4 squared, 1.4 cubed. If you do it 12 times, you get 1.4 to the power 12. So, the height of this rather tiny rectangle is 56.69 units of vertical height. Okay? By the way, what you are looking at here is not drawn to scale. Because no way this is 56 times larger than this. I draw it compressed so that I can show it to you on the page. Because otherwise this is going to be 56, it's going to go out to the next room. It's way too big. That clear? Now, quickly, let me get the ideas clean in here. You are seeing 2 to the power 12 rectangles that happen to have very tiny bases, all equal to 1 divided by 2 to the power 12. Allow me to go back to be certain that you understand. There are 1, 2, 3, 4, 5, 6, 7, there are 8 here whose bases are 1/8, right? Here there were 4 whose bases were 1/4. If I do it again, everything happens in powers of 2 because I'm dividing by 2, dividing by 2. So the next time I'm going to have 16 pieces and the length of the base is 1/16, right? So you do that 12 times, and this is what you get. So there are 2 to the 12 pieces that are very thin because the base is 1 divided by 2 to the 12. Now, how much is 2 to the 12? I can tell you, there are some numbers I know. It's 4,096. So you are looking at 4,096 rectangles. I cannot rise up, but I'm going to do the following. Imagine that you see my hand way up and I touch this object from the top. I'm going to respond to what happens. I'm going to say, ouch! I'm going to be pricked by those very thin and high elements that you have there. Okay? So I want to baptize those elements, and I'm going to say they look like thorns. Okay? So you repeat this 12 times and you get a collection of thorns. In other words, very small elements that are very pointy, as shown there. Total 4,096. There is one and only one that happens to have the most possible mass, which is, you repeat this stuff 12 times. Here you did it 3 times. P, P, P. And you keep going. P, 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 12 times. So this thorn contains P to the power 12 of the mass. Right? Now, in here, it's hard to count, but all of a sudden you realize there is one here, but there are more that are at an equal height lower than the original. Let me write this so that you see. The largest, P to the 12th. The second largest, P to the 11th cube. The next one, P to the 10th Q squared, and so on. That is how these things are going to happen. So, these guys, they all have this mass. These guys, they all have this mass. Okay? Immediately you look at that and you say, gee, there are more of these than of this. Right? I can tell you the numbers because I have memorized it for this case. There are 12 here that correspond to P to the 11th cube. And there happen to be 66 here that corresponds to the next level of thorns. Okay? Of course, this continues. Huh? this is not the end of the story. The next one is p to the 9 q cubed. Which one is that? This one. Right? There are more of these than this. And there were more of these than that. So there is a variation of how many values you get. Okay? In the other extreme, which you cannot visualize because values are too little, you have q to the 12th. Over here, there is a dot at the end of this that happens once. It's q to the 12th. That comes from q, 12 times, so you get q to the 12th. Adjacent to it, you have p q to the 11th. By the way, there are 12 of these guys, as there are 12 of these guys. There are 66 of these guys, as there are 66 of these guys. What you get is something that is symmetric. Okay? The smaller, the larger, and they go woo in terms of how many values are there. 1, 1, 12, 12, 66, 66, and keep increasing. Okay? That's what you get out of the calculations. So, let me repeat. You do this game, and I'm doing it slowly so that I could be understood. The game generates thorns that are arranged by layers. You can see the layers, right? There is the highest layer corresponding to this, the second highest corresponding to that, the third largest, the fourth, the fifth, and so on. How many layers are there? There are 13 layers. Because it's from p to the 12th to q to the 12th, this is p to the 0. And if you count, it goes from 0 to 12, and from 0 to 12 there are 13. So there are 13 layers in this thing. All right? So the game generates layers of thorns. Not all layers are created equal. Right? There are some layers that are very dense, like the one that I'm showing here below. This is denser than this one, which is denser than this one. Okay, so there are the layers have different densities associated with them. And the density increases as you go inside the object from side to side. Yeah? Okay, it's a bit technical, but hey, I'm a teacher, I want you to understand. All right? So, there is a peculiarity, though, that I want you now to pay attention to, and that is the fact that if you concentrate on a given layer, let's say this one, there is a gap between this thorn and this thorn, and there is a gap between this thorn and this thorn, and there is a gap between this thorn and this thorn. In other words, things don't stay together. And the reason is because you cut by the middle and you do the operation of 70% to one side and 30% to the other, so things don't stay together. What I just said is true for any other layer. So you look at this layer, and between these two there are values that are not on that layer. Between these two are values that are not in that layer. So all the layers of thorns are intertwined. That's the word that I want you to realize. By the way, it may appear that you say 70% to one side, 70% for one side, that you would imagine everything that is big is going to be in one side. It turns out that big and small are intertwined within the object. So for instance, before this big spike, there is almost nothing here. Okay? So let me summarize. There are layers of intertwined thorns that this game produces. Now, if you concentrate on the points from which the thorns emanate for a given layer, because the thorns don't touch, the points in question cannot touch either. Question: what name do we have for a collection of points that don't touch? It has to do with our friend Cantor. This is called? Huh?
Cantor set.
There is the other word associated with Cantor set that I wanted to say. This is dust. This is dust. So what I'm basically trying to tell you is these thorns emanate from one dust set. These guys emanate from another dust set, and so on and so forth. So there are many dusts. Of course, for you guys that have been in this class in the past week, dust is an example of a fractal, and because there are many dusts, this object is going to be known as a multifractal. So it's a multi-dust. Okay? So this is a bit technical, but it's important for later. All right? So the support of the spikes is dust. In other words, the spikes do not touch if they come from the same height. So they come from a succession of points that don't touch, ably known as dust, because when you encounter something that has no cohesion, you blow it out because it's dust. And that's precisely the thing that you get. To summarize, if I were to place myself on top of these thorns, immediately I'm going to realize that this is a very hard to walk object. All right? By the way, this could be done much quicker without interacting. But, you know, I prefer to do the interaction so that we are together and you understand what is going on. By the way, this is done 12 times. What am I going to do? Hey, do it many times. Infinitely many times. So, instead of getting 13 layers, you get infinitely many layers. Okay? And instead of getting a certain number of dusts, you have infinitely many dusts. Okay? So the title for this to be known as a multifractal is a good title. So, game number one, summary, the game of imbalances. The message after doing all of this is, it produces thorns that don't touch, arranged by layers that are defined based on dust. So there is dust, thorns that emanate, making up the whole object. Clearly, it's very difficult to walk. So imagine that I happen to be here and I want to visit a friend at the same height. I need to go down and up and up and down and up and down. It's not as simple as, hey, how are you? Okay? Another thing that I ought to say is that if you happen to be on a very tall location, this is a rather precarious place to be. Okay? Game number one. So, let's do game number two, which we can do much quicker than this, as it has to do with the first game. So, this is a second game for kids. It's also done with modeling clay. So, here is the bar of modeling clay. The difference is that I'm going to cut the modeling clay by the middle. So I cut it by the middle. I take this piece and I squash it to the left. I take this piece and I squash it to the right. Leaving a gap as shown. So for the example, this is what we did last week in terms of the Cantor set. So a third, and a third, but there is nothing in the middle third. Okay? Question quickly, what is this height? It's the same formula, right? It's how much? No, 50% is the mass. The question is how much is the height? You know, this was squashed to get this, and this was squashed to get that. So it's higher. The question is how big it is. 1.5, right? 1.5, because it's 1/3, so 3 times 50% is 1.5. So the previous game it was 1.4, now it's 1.5. All right? So is it clear what this game is? So take the bar bowling clay, go to the middle, square to the left and the right, repeat. Boom. Okay? So dot, dot, dot. This is going to be another multiplicative cascade. It's the same kind of thing. The difference is that this one is not going to generate layers. Everything here is in one layer. Because as you can see, all of the rectangles that you saw defined happen to have exactly the same height. Right? Yes? By the way, it's a multiplicative thing. A third, this is a third of a third, this is a third of a third of a third. So everything is done exactly in the same proportions. If you repeat this, let's say 10 times, you are going to get filaments all the same length that don't touch, because by definition no two rectangles touch. And by the way, if this is something that you do in your kitchen, this would be a good way to do perfect spaghetti. Okay? All the spaghetti exactly the same height and everything. Okay? So, second game for kids. So this generates equal thorns over a single dust. Why am I introducing this to you? Because I'm going to relate this second game to the first game. Okay? So, how do I relate them? If you vary the size of the hole by which you start, let's see what happens. If this size of the hole is tiny, you're going to get a bunch of spaghetti that are closely bunched. If you have a value of the hole which is huge, you are going to get the spaghetti that are farther apart. So for those of you that were here last week, the dimension of the dust that you get depends on the size of the hole. The smaller the size, the more bunched the things are, and vice versa. Okay? So, if you go back to the first game, you realize what I have been saying on the board. This is more dense than this, but the one that follows is yet more dense than that. So you could play the second game with an appropriate hole so that you mimic the structure observed by the first game. So if you want to capture a layer that is very dense, what you need to do is you take a very small hole in the second game. If you want to capture something that is medium size in terms of the density of the thorns, you take a size that is not so small to capture that. Okay? So, the two games turn out to be intimately related. So, let me repeat the games. Game number 1, the game of imbalances. Game number 2, I haven't baptized it, is the game of holes. What you see here is what happens if there is a hole and that hole propagates in the same proportion again and again and again. Okay? What is it that the game of holes generates? Thorns and one dust. But by varying the size of the hole, you could mimic the structure on every one of the layers on the first game. Okay? There is one word that comes to my mind that I should tell you. The two games are games of division. Okay? They are divisive games. One division like this, and the other division like that. Alright? Okay, so this was quick. So, in order to conclude, so that you start seeing important implications, there is yet another game that I need to teach you so that you could visualize something associated with the games. And this is in response to the question posed up there. Where is the modeling clay? You see, this is game number 1. This below is game number 2. If you look at where the mass is on the left, this goes forever because you repeat this infinitely many times. So these forms are going to go to infinity. Okay? So it's not a good way to visualize something that goes to infinity. By the way, the highest thorn goes to infinity. The second highest also goes to infinity. It's just that it goes to infinity slower than the first one. All of these layers eventually go higher and higher and higher and higher. Okay? So people in math and people in physics and even in hydrology, my science, you say that is not a good way to portray where is the modeling clay. Instead of that, which I'm showing here for 12 values or something like that, this is not doing it infinitely many times. Instead of portraying it like that, I'm going to portray something similar to the right. It's similar in the sense that all the mass is going to be portrayed, but instead of how much value I have here, the question is, how much do I have from the beginning to here? So I want to accumulate the modeling clay. And I'm going to define this quantity C of X, C for clay. So how much clay is there from 0, the beginning of the object, to X? Allow me to explain this again. From 0 to 1, in here, from 0 to 1, I changed the size of the scale so that it would be nice looking. But the horizontal on the left is from 0 to 1, and on the right is also from 0 to 1. Okay? So, C of X is how much modeling clay is there from the beginning to a value of X that I'm going to move as I transfer the object from left to right. Okay? That's what it is. So, let's try to do the one in the bottom. Okay? This is too high for me to touch it, but imagine that I have a finger that is placed at this location, which is the beginning of the object. That's 0. So I have a finger right there. And imagine that I tell you, X is going to be the red dot. And I'm going to ask you the question, okay, how much modeling clay is there from the finger to the dot? So, question, how much modeling clay is there from the finger to the dot if the dot is here? How much modeling clay is there from beginning to the dot for this particular game? How much? Let me ask you an easier question, okay? The finger is at the beginning, and the dot is at the beginning. And I ask you the question, how much modeling clay is there from the beginning to the beginning? 0, thank you, 0. So, I'm going to plot your answer here. You see, this height is from 0 to 1. This is 0, and I place myself at the beginning, which is 0. So, this point that I'm touching is 0, 0. Also known as the origin. Okay? 0, 0. Are we together? Question. You are seeing my finger at the beginning, right? How much modeling clay is there from the beginning to the end? 1. Why? Because of the principle of conservation of modeling clay. All the clay is there. So, if I put myself at the end, this height is equal to 1. Are we together? By the way, this is going to be true also for the other game. You know, if I put myself, the finger and the dot here, 0, 0, and if I put myself at the end, you get 1, 1. It has to be because of conservation. Now, let me ask you the question again. The finger is at the beginning of this, and the dot is here. how much modeling clay is there from the beginning to the dot? Come on, you're being recorded. You should know the answer.
Half.
Half. Yeah, it is half. Why? Because the second game was I cut by the middle, so I placed the dot in this gap, in this hole. So consequently, the amount of modeling clay from beginning to that point was 0.5, 50%. Correct? 50%. What about this point? Half. This point. So everywhere that I am in the gap, the height is equal to half. Oh, that is what this is plotting here. You see this shape here, horizontal? The height of this horizontal is precisely the half. You see that? Precisely half. By the way, this is a plateau. This is a gap, and this is a plateau. Okay? Now remember, this game repeats and repeats and repeats. So, I ask you, how much mass is there? My finger is at the beginning. From the beginning to a point in this gap.
Quarter.
A quarter. Right? It's a quarter. Oh, so you say a quarter. I see it. It's a quarter. Right? If I place myself over here, how much? 3 quarters. 1 quarter, 2 quarters, 3 quarters. Ah, I plot it here. Okay? The length of the first plateau is a third. The length of the next plateaus are a ninth. Because everything is done in the same proportion. Are we together? Can I say etc.? Etc. means you get this object. Right? So, you have an object that is filled with plateaus. Horizontal spaces all over the place. Okay? Let me ask you the same kind of a question above. Okay? So this is the first game, the game of 70-30. So, question. I place myself at the middle and I ask, how much mass is there from the beginning to the middle? How much? Huh? The game was 70% to the left and 30% to the right. So the question is 70%, right? You need to see it again. I can show it to you again. But this is what generated the object, 70 to the left, 30 to the right. 70 of 70 to the left, and down, 70, 70, 70, etc. Right? That's how it was built. Okay? So I asked the question, what is the amount of modeling clay from 0 to the middle? So you say 70%. So I place myself here in the middle, and I go up. You see this notch here? The height of that notch is 70%. Okay? So it's done on the computer, it's done accurate. Not always, but in this case it is. And then I ask you the question, how much mass is there from beginning to a quarter? How much mass is there from beginning to a quarter? The answer is 49%. Oh, so you put yourself here at a quarter and you go up. And you get another notch, and the height of that notch is 49%. And that is how you get that cloud. Right? It looks like a cloud. Okay? Moreover, I tell you that cloud looks like a cloud of dust. When there is an explosion, when a volcano does its thing, or when we humans destroy buildings and things like that, you get an object that is so shaped. Okay? By the way, what was united gets pulverized, becomes dust. So at the end you get a cloud of dust. Okay? That's what you get. Okay, so this is a summary. So you get notches above and plateaus below. Right? Now I have some fundamental questions about these objects, which I'm going to baptize in a second. Okay? So, I'm going to ask a question that I'm going to answer essentially by myself. And the question is this. Imagine that I'm here and I want to go there, and I need to walk this pattern. The question is, how long is that pattern? I can ask the question. You could guess. How long is this pattern? And for that matter, how long is the shape that gives the cloud? Finite, infinite? Some people think, oh, this should be infinite. It's not. So let me answer the question, and you will argue with me if you disagree. So, if you want to walk this object, by the way, that's a pretty strange looking object. The white part and the black part are identical copies of one another. Okay? You could do tiles with this and actually get a nice effect because of that particular property. Okay? Okay, so if you want to walk from beginning to the end this particular object, you need to walk all the plateaus. Right? This object has plateaus everywhere. A third, a ninth, a 1/27th, blah, 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 forever. Okay? If you were to add the length of all the plateaus, the length of all the plateaus is equal to 1. It's equal to 1. Why? Because this is the length 1, which is the same length 1 there. The length of all the holes is equal to 1. Why? Because you take all the holes and you take out the dust. The dust doesn't add up any length. So the length of all the holes is equal to 1. Consequently, the length of all the plateaus is equal to 1. Yes, sir? Now, I need to go up or down, depending on where I am placed in this object. Consequently, the distance between beginning and end for this object has to be equal to 2. 1 unit horizontally plus 1 unit vertically. Right? Is that clear? Now, important. Imagine that instead of a third for the hole is smaller. 0.05, small hole. Do I still get the same property? So, you take a smaller hole. Clearly, by repeating this thing with the smaller and smaller things, you are adding holes, gaps, and you are always doing like this, so things are going to go higher and higher and higher. So you are going to get something that looks like that with the smaller holes. At the end, when you accumulate, you are going to have plateaus everywhere. If you happen to have plateaus everywhere, the length is equal to 2. By the way, I hope that you get this. You do it like this, the length is equal to 2. You do it like this, the length is equal to 2. So you say, hey, but I only use a small hole. So are you telling me that a small hole is as bad as a big hole? Yeah, that's what I'm telling you. Okay? That's it? By the way, we people oftentimes, when playing these games, because by the way, these games are games that we play, we say, oh, but I'm not as bad as somebody else, because somebody else is really having a big gap. I only have a very tiny gap. Well, in terms of the properties of these objects, provided that there is a gap, the length of this is going to be equal to 2. Are we together? Okay, good. What is the length of this cloud? The answer is, again, in order to walk the cloud, you need to walk the notches. A notch is something like this. It's a rather awkward thing for me to even show. It's horizontal on one side and vertical in the other. Okay? The key is that horizontally is flat. So you need to walk all the notches, and that object has notches everywhere. It's notchy. As a consequence, you need to walk them all, so it's 1 plus 1 equal to 2. Question. This is what you get with 70-30. What about 55-45? 55-45? Any better? 55-45? Well, you would argue, well, it's a bit better. I mean, there is less of an imbalance than with 70-30, 55-45. But 55-45 is going to generate, through the same multiplicative cascade, an object like this, for sure. And when you accumulate, that is going to give you another cloud. Not exactly this cloud, because this value is not 0.7, but it would be a value of 0.55, which is smaller. But in between, you get the same mathematical structure. So, 70-30, pretty bad. 51-49 is as bad in terms of the length. The length is equal to 2. Okay? Put together? Okay. So, these objects on the right, everywhere you look are flat. Okay? They are flat. And they have a very ugly property, and that is that you cannot draw tangents on them. By the way, don't we all like to go off on a tangent? You know, sometimes the situation is complicated and you want to go off on a tangent. If you happen to be on these objects, that's impossible because these objects don't have tangents. Whenever you have the notch, horizontal, vertical, everywhere, you cannot put a line drawing a tangent. And the object in the bottom, at the corners of all the plateaus, you cannot draw tangents. Okay? So these are very weird looking sets that don't have tangents. This is the property that I just explained to you. The distance from beginning to the end is equal to 2, always, provided that there is an imbalance or provided that there is a hole. That property is universal. Okay? By the way, these ideas appear perhaps a bit rigid. Game number 1, imbalances. Game number 2, holes. You say, hey, why don't you combine them? Right? So you say, okay, I did. I just did it with my hands. Okay? And some other people say, hey, why do you use 70% all the time? Why don't you spice it up? Make it 70% sometimes, 60% other times. You know, do it randomly to some degree. Okay? By the way, those kinds of things are models of physics that people use because people realize that this is division and there are manifestations of division in many aspects of what we do in science, and this is too rigid to get those. So you combine the games and randomize. The message is, it doesn't matter. If you combine the games and you randomize them, the distance that you get on the accumulated object associated with doing this is always going to be equal to 2. Okay? Okay. So, imagine, poor me, I'm parachuting on this object. Okay? So, what happens to me? Could you predict what will happen to me? Of course, I would land on a plateau because, you know, this place has plateaus everywhere. Okay? I mean, you didn't know that I was going to land on the one in the middle. But, okay? So, I land on a plateau. From my perspective, having landed on this object, I'm thinking, gee, I have landed on flat land.